All right, welcome back everybody to Bio 72 PCR. And this week we have Richard Weeks as a guest lecturer, and he's going to be talking about downstream processing and distack centrifugation. I've really been excited about this because later in the course, we're actually going to be doing this. And certainly if you stick around in the spring in 79, we do a whole section on downstream centrifugation, sedimentation, all that stuff. So really excited to have him here, and we're going to let him take it away.
Hi guys, I'm Richard Weeks. I worked for Alfa Laval for 42 years, and then I retired and they asked me to stay on as their rep. So I'm still here working with customers, solving their problems, separation problems, and hopefully selling equipment eventually. That's what they pay me to do. I'm a sales guy. So to get started here, a little introduction. A guy named Gustave de Laval created the company back in the 1878 was when he got started. He actually built a plant in Poughkeepsie, New York. That's actually where I started. His initial concept was to create a cream separator, separate cream from milk. And back in the day, it was a hand crank type. And eventually that was for bowls like this big. So every farm had a cream separator. But eventually the bowls got this big and you couldn't crank them anymore. So he did a lot of work on steam turbine designs, and just a really clever guy. Started lots of companies and had lots of patents, but just a really clever guy. So this is the topics of discussion today. We're going to talk basic separation theory, which Stoke's law. It's all about Stoke's law. And I'm going to ask you questions, and I hope you'll ask me questions as we go along, just so we can all learn more. So we're going to talk about solids ejecting centrifuges. That's the main discussion. And they can be either liquid-liquid, where we're separating either oil from water or water from oil or milk from cream. And a clarifier type is where we're just taking solids out of a liquid phase. We're going to talk about a spin test evaluation where we just do test tube spins, and that helps us to evaluate what a large scale machine will do. We're going to talk about what we do with small machine testing after we do spin tests, and how we scale up to large machines. We're going to talk a little bit about, so there's solids ejecting machines, and then we also have a couple of designs where we continuously discharge the solids, which are good, where your feed solids are high, like above 10, 15, 20% by volume. We're going to talk about low shear designs, just a little discussion on centrifuge clean in place. Just thought I might mention to you, for Biotech, we now make a single-use centrifuge, which is all plastic, which again, if you get into the biotech industry, you might see that. But we'd have a little discussion on Decanter centrifuges, and then just some of the other products that Alfa Laval manufactures and sells to the industry. So everybody can hear me okay and hear me through my mask. And okay, basic separation theories. So everything in the centrifuge world is based on Stoke's law. And in Stoke's law, the gravitational settling velocity is equal to the diameter of the particle squared times the difference between the density between the liquid and the solids, or the liquid and the liquid if we're split in two liquids, divided by viscosity times some gravitational force. On Earth, that's 1. But so looking at this formula, what do you guys think what can I have an effect on as a centrifuge guy? What do you think I can do? I can help you with G-force. Some of our machines are up to 15,000 Gs. Yeah, most of them are in the 5,000 to 8,000 G range, and G-force is part of the discussion, but not the total end all, let's say. So what else? What else do you think? Looking at this formula, what else might we be able to affect based on the formula? Can't really help the densities, right? I'm sorry, what's that? Yeah, that's the same as G-force, but what thing we can work on is viscosity. Sometimes if you heat it like an oil, it's very viscous at low temperature. So if you heat it up to 70, 80 degrees C, viscosity reduces, so that can help us make separation. But what is the biggest factor in the formula? And this is the most important thing. Particle size. Absolutely. And why is that? Because you're squaring it, right? So for a disk machine, like yeast cells are like, let's say 8, 9 micron, that's a big cell for a disk type machine. But bacteria is 1 micron. And you know, cell debris might be 0.5 micron. So, and the fact is we're squaring those particles. And with that, greatly reduce gravitational settling velocity. The machine that Doug is aware of, we have a unit called the Clara 20. The Clara 20 on bacteria might do 1 liter a minute, and on yeast might do 10, 15 liters a minute, depending on the solids. So particle size. And I talk to even really smart PhDs, and sometimes they don't get it, but it's all Stoke's law. It's very simple. So can't argue with Stoke's law. So. And so as you know, as particle size increases, obviously separation efficiency increases. As density difference increases, separation efficiency increases. As viscosity increases, the reverse. So I always like to start out my discussion with a gravitation, continuous gravity settling tank. And because that's a pretty easy concept, 1G is all we work with in a gravity tank. And the throughput capacity on the tank is equal to the gravitational settling velocity times the settling area. And at some flow rate, you're going to put to a settling tank, at some point, you're going to have so much flow going through the machine, it's not going to have time for G-force to make the separation. So at some point, you're going to lose all efficiency. And so how do we make a gravity settling tank more efficient? We can increase the efficiency of a gravity settling tank by adding what we call buffer plates or lamella plates. And basically what those plates do, as the liquid traverses up through these plates, they don't have to go through several inches or several feet of liquid to make a separation. They just have to travel down to these plates and then eventually go down to the bottom of the tank. So they use this technology in gravity settling tanks all the time. This gives you more surface area to make separation. So if we take this concept, and you guys see where I'm going with this whole thing, we're actually making a continuous unit, a continuous bowl unit that spins at 5,000 Gs or 10,000 or 15,000 Gs with all these lamella plates in there to give you lots of separation area for separation. Anyway, you travel in through the feed pipe where the arrow's coming in. You go underneath the distributor up into those discs. G-force is throwing the solids out to the underneath side of the disc, and they accumulate at the bowl wall. And this is what the disc looks like. They're very thin. They're about 0.5 millimeter apart. So that makes a centrifuge much more efficient. You know, all these discs are piled on top of each other. Small machine like the Clara 20 might only have 80, 90 discs. A big giant machine like used at a winery or fruit juice plant might have 300 or 400 discs and much bigger diameter, kind of like this big one on the floor here. And we'll talk about those when we get there. But these discs are normally just about a 0.5 millimeter apart. Your liquid's traveling up towards the center of the bowl and out. Your solids are traveling to the disc to the outside of the bowl. And this would be, you have a question? Oh, okay. Any questions are welcome. So, but this would be a very simple machine where the solids would stay in the bowl, and then we'd have to manually remove these solids. And that's okay if you don't have a lot of solids in the feed, but if you have a lot of solids, then we want to talk about a solids ejecting machine. But typical applications in the fermentation industry: baker's yeast, alcohol production, single cell protein, algae. Do a lot of work in the biotech industry on E. coli normally. Another term, CHO cells, Chinese hamster ovaries, are popular for biotech companies to express the drugs that they want. Starting to work with some of these new companies that want to make cellular meat. So we're working with those guys. In the biotech industry, they don't care about the cell. With CHO cells, it expresses the product into the liquid phase, and the bad stuff is inside the cell. So you want to minimize shear on those cells, so you don't have to go downstream, go through a lot more work to get the bad stuff out. You can not shear the cells. In the animal cell side, they want the cells themselves because they're going to make chicken McNuggets or hamburgers or whatever out of this stuff. So we're going to first talk about solids ejecting machines. And this is a typical Alfa Laval, or our competitors' design is fairly similar. The bowl, you can see that's outlined by the red part. The yellow inside the bowl is what we call a sliding bowl bottom that moves up and down, whether we want to eject solids or keep them in the bowl. It's driven by a spindle, which goes down either to a worm gear assembly, which is driven by a direct drive motor, or some machines are belt driven, but same, you just need a driving force to spin that bowl. The frame to support the whole unit. You can see the frame hood is the cover that goes over the top of the bowl, and in between you can see an area where we can put cooling liquid. And that cooling liquid does not cool the liquid inside the bowl. It's mainly to cool the covers, because as the bowl spins, you get a lot of frictional heat that's developed. And it could actually make those covers like, 100 degrees C, where product would burn on the covers. So that's mainly when you eject the solids, you don't want them to stick to the covers, keep the covers cool. And see that thing in the back, that's a cyclone. So when you eject the solids out, that cyclone is just a place for the solids to spin around and drop down below the unit. If the cyclone wasn't on there in the back, it would shoot 100, 200 feet across the room. It has a lot of energy coming when you discharge it out of the bowl. So as I mentioned before, so disc machines can either be for liquid-liquid separation. When we talk about liquid-liquid, we normally either talk about a purifier or a concentrator. A purifier is what they use. Every ship that goes out to sea has a half a dozen purifiers on it to purify and take the water, the condensation out of the fuel. The concentrator is more, so when purifiers, we have mainly oil with just a little bit of water. Concentrators, it's mainly water with a little bit of oil, and we're trying to concentrate that oil phase. And the other option, and where most of the applications that I see, are liquid solid separators. Again, so if we look at a purifier disc stack, so in the disc stack themselves, there's holes. So you see those holes, that's where the liquid creates the interface between the two densities of liquids. So in a purifier, normally the holes are close to the outside. And on a concentrator, the holes are normally closer to the center. You can see those holes there. That's where the interface between the two liquids would come up through the disc stack. I mean, we could probably go into more discussion on liquid, but you're not going to see them all that often. I think the main focus should be on clarification duty, where we're trying to remove solids from liquids. So in a clarifier, the solids are going to accumulate at the bowl wall. And at some point, you're going to fill up this area outside the disk stack. When that happens, then you want to tell the bowl to discharge. We say shoot the solids out of the bowl. This blue under here is water, and that's what holds the sliding bowl bottom up in place when the bowl is closed. When we want to discharge the solids, we very quickly evacuate that water underneath the sliding bowl bottom. It allows the bowl to drop down and close very quickly. In the old days, the mechanisms to shoot the bowl were very slow. So you would evacuate everything in the bowl, everything in the disk stack, all the liquid. If it's a 2.5 liter bowl like the Clara 20, you would evacuate everything. But with the new machine, the faster discharges, we just want to eliminate that 1 liter at the bowl wall. And that'll give you the driest solids as well. Hopefully my animation works. This is the one I really like. Some machines are top fed. This machine is actually bottom fed. And I like this animation because it shows how the bowl closes at the beginning. And then it actually shows how the solids discharge. So let's see here. Okay, so you see blue is the water. Okay. Now we're evacuating that water. The sliding bowl bottom is going to drop down. We're going to reintroduce water and close the bowl. Now we're going to start to feed the machine. This is actually showing a liquid, but it also is showing the solids accumulating in the bowl. You can see time to discharge, 3, 2, 1. That's how the solid discharge out of the bowl at full speed. We don't slow the machine down. It happens at full speed. And in order for solids to come out of a solids ejecting machine, they have to be 70 to 80% by volume solids. They have to be flowable, like a thick milkshake material. If you try to get it too dry, it might shoot out of the bowl, but it won't come out of the covers. It's got to be able to flow. I mentioned, we do a lot of work with spin test tube centrifuge like you have here in the lab. And what does that tell us prior to running an actual test of centrifuge? So I have a test unit that creates 10,000 Gs, which is fairly similar to most disk machines out there. And I know if I spin that at 30 seconds at 10,000 Gs, it'll be a very easy separation. And with that, I would expect a high flow rate through a continuous centrifuge. If I don't get good clarity at 30 seconds, then I make a 60-second spin and look at that. Look at the supernatant, how clear it is. And still at 60 seconds, if I get good clear supernatant, I expect good separation and a reasonably good flow rate. As if it takes 90 seconds or 120 seconds to get clear supernatant, then that's going to be a difficult separation. So that means very slow flow rate. So normally, like with bacteria, we're normally in that 90-second to 1 second, 120-second spin time to make separation. And this obviously is a very difficult separation because you can see for 30 seconds, hardly anything. And we had to actually get to 90 seconds before we started to get a reasonable split. This stuff makes sense. Okay. So once we determine, kind of expected separation based on spin tests, and we do a test with either an LAPX 404, which is the Biotech machine over there. Yeah, this is one you saw at Bio, right? Yep. So that's the Clara 20. You can see the Biotech unit has much fancier control panel and has a lot more stuff because the biotech guys like to put a lot of stuff on their unit, whether they need it or not. This is a very simple unit. You have to adjust flow rate manually. You have to, it's only timer discharge. You have to adjust back pressure on the unit. So it's a very manual operation machine, right, Doug? I mean, but it's a, it's like driving a stick shift versus an automatic. It's a real experience. Go ahead. The stuff here. So yeah, this would be more of a food industry unit. Yeah, the biotech unit might have higher surface finish, has a lot of documentation that they want. That's the main difference. Do both machines clean? Yes. Do they need polish? Maybe, but probably not. It probably clean just as well. But the biotech industry likes to have every bell and whistle they can have in a, it used to be a spec on a biotech machine, used to be 50 pages, and that was 30 years ago. And now the spec comes in 500-600 pages of really stuff that really doesn't add much. But so the skids are fairly compact, about 5 feet long, and less than 6 feet high, and normally 2.5 feet wide. The one at Pal Bio is a little wider, but normally it'll fit through a normal doorway at any lab. So it's very easy to get in and out of the room. The Clara 20 generates up to 11,000 Gs, has a VFD on it. So if we want to reduce G force, we can do that. It's what we call a fast partial discharge. It shoots 1 liter every time we discharge. Has a centrifugal pump to pump the clarified liquid away. All stainless contact parts. Very quiet at 72 dB. Solid space is 1.1 liters. Every time it shoots 1.1 liters. Again, we talked about typical performance on algae or yeast. We might do 10 to 20 liters a minute. On whole cell E. coli, it's normally like 1 to 2. Very high recoveries of the solids. Normally 95 to 99% recovery, which is good. Typical solids concentrations are to 60 to 70%. That's the milkshake material that is discharged. Normally 70, very doable. Some products we can get up to 80. Feed concentrations are 0.5 to 5%, but I have run as high as 20% on that unit, which is a lot of solids for a solids ejecting machine normally. So we normally recommend a test to determine your production needs, because normally people want to scale up to, Pal Bio has like 200-300 liter capacity. They want to go to 2,000 or 20,000. So we want to be able to have the capability to scale up to large plants. How do we do that? So during the test, we determine the optimum flow rate, whether it's 1 liter a minute. We know that flow rate, if we start carrying over solids, that's just above the optimum flow rates. We have to bring it back down. So we know Q is the optimum flow. Sigma is the area equivalent of the centrifuge. In the case of the Clara 20, it's like 5,000 square meters. Sigma is based on how big the bowl is, how fast you spin it, how many discs are in the unit, the angle of the disc. So all that stuff goes into the sigma. Our biggest machine has a sigma of like 400,000 square meters. So that's a big tank. It's a big equivalent tank. So once we determine, these are food grade machines, but once we determine we can do 1 liter a minute on the Clara 20, we'd expect to do 4 liters a minute on the Clara 80, 17 liters a minute. And again, if it's 2 liters a minute, it's just a multiplication factor. And like I say, unless it's bacteria, if it's yeast, we might be able to do, humongous 600 liters a minute, but probably not, because the other limitation of a centrifuge is not just clarification, but how much solids you can handle, especially with solids ejecting machines. That's what we're going to talk about right now. So So a centrifuge, like we just discussed, solid ejecting centrifuges, they're clarification limited. When the feed is too high and you start carrying over solids, you just readjust your flow rate to make sure you're within the, you're not over pushing the capacity. But the other key thing is it's also solids limited. If you have a 1 liter bowl and you're trying to feed it 20% solids, like they often do in the biotech industry, then the limit is not clarification, it's how much solids you can handle. And once you fill that 1 liter space up at 70% solids, you have to discharge. And that's one key thing, again, that a lot of people just don't understand. You can't put more than 1 liter in that small machine. And the big machine might have a 30 liter solid space, but still, once you fill that 30 liter solid space up, you have to discharge. So in biotech, they're very concerned about shearing the cells at the inlet. Not so much bacteria, because bacteria is not very shear sensitive, but CHO cells are very shear sensitive. And the highest point of shear is at the inlet. You're bringing it in through the feed pipe at the top. And as you hit the bowl, it has to come up to bowl speed right then and there. The other problem with top-fed machines is you have the opportunity to pull in air around the feed pipe. And a combination of air with that high shear inlet just creates phenomenal shear. You might take, like CHO cells could be 18 micron. You can turn those into submicron particles, depending on the type of feed zone that you have on the machine. So what we call the traditional wing inlet was a design from probably back in the 50s and 60s. It looked like a whirring blender at the inlet. And the idea was to bring everything up to speed quickly. It created a lot of shear on shear sensitive cells. It made these nice big particles into submicron particles that were much more difficult to separate. And it'd be like having a tank. If you ever had a tank and you're spraying a hose on the top of the tank, you create a lot of foam. Foam's over the top of the tank. So the idea of what we call the disc inlet was to submerge the feed pipe. So it's underneath the liquid. And that greatly reduces the foaming and greatly reduces the air coming into the unit. The other thing, as Doug knows, we can also put back pressure on this pump that pumps it away to minimize the air in the sight glass so it looks clear. But once it comes out the other end of the pipe, it still foams like crazy. So we're not really eliminating the air, we're just kind of reducing it. And with the Alfa Laval design, the bottom fed hermetic design, you have a mechanical seal at the inlet, a mechanical seal at the outlet. Absolutely no chance of picking up air across the unit. Absolutely no chance. So you feed in through the bottom, through the hollow spindle, and out the top of the unit. No air pickup. Very gentle on your cells. Why is low shear important? If your cells are shear sensitive, then it's important. If they're not, then it's not. If you're shearing cells at the bowl inlet, that can create smaller particles that are much more difficult to separate, as we said. Alfa Laval designs optimize shear reduction. So there's some other designs that we have for high solids. So right now we're depending on either timer discharge or turbidity discharge, telling the machine to shoot with a solids ejecting machine. But we have a couple different designs, nozzle bowl designs that are continuous discharge of the solids. So what we call the SX design, you have nozzles all around the periphery of the bowl. And the limitation of that is the nozzles are small and they're prone to plugging. If you get big particles that can plug the nozzle, then you have imbalance problems. The other issue with peripheral nozzles, you're at the highest point of G-force. So it's very difficult to control the flow through the nozzles. It'd be nice if those nozzles were closer to the inside of the bowl. So now you're at a lower point of G-force. How we handle that is what we call the UX or the vortex nozzle design, where the nozzles are right at where you see the green ends there. That's where the nozzles are located. In the UX 510, there's like 8 nozzles all the way around the ball. We'll talk a little bit more about the vortex nozzle, but in that design, wait till the later slide. The other design we call the backfuge. And the backfuge is where the centrifuge actually behaves like a liquid machine, and your solids behave like a heavy phase liquid. The name backfuge came from bacteria. If you spin bacteria in a test tube, normally if you turn the test tube over, the solids pour out. Certainly if you spin CHO cells in a test tube, turn the test tube over, cells pour out. So they're very soft, and they can behave like a liquid phase almost. Yeast doesn't work so well in a backfuge because if you spin yeast in a test tube, packs hard. You actually have to dig the solids out. So for a backfuge to work efficiently, the solids can't pack hard in the test tube. That's kind of the rule of thumb. So with the vortex nozzle, based on the very high pressure of the solid, or the high G-force and pressure at the bowl wall, it's forcing solids up the tube into a vortex nozzle. And then that vortex nozzle has a spin chamber. We'll show you the next slide that shows you the spin chamber. But it's kind of like a self-regulating nozzle. It then enters into this chamber. This is a stationary pickup tube and continuously discharges out of the unit. This unit was designed for yeast in mind, baker's yeast. In the old days, you either had peripheral nozzles or you had mechanical nozzles that you had to adjust, but this made the machine much more friendly for processing baker's yeast. This also has a CIP capability where you can overpressure these springs for discharge of CIP liquid out of the ball. Again, wherever these tubes are, you have a place to clean during CIP. These nozzles look like. So if when you come into the nozzle and it's showing low viscosity, that means it has to make several passes around the nozzle before it comes out the center of the nozzle hole. If it's already fairly thick and high viscosity, it might just make 1 or 2 passes before it comes out. So it's within a range of, as long as your feed solids are consistent, as long as your flow rate stays consistent, these nozzles perform very well, and they work within a range. But if the machine's set up for 30 gallons a minute and you try to run it for 10, you're probably going to have to adjust the nozzle side, or you might have to adjust the vortex chamber size. So it works within a range. But most people, once they get set up and they keep the tank agitated, just if your tank's not agitated and you get 10% now and 30% later, that's not good. It's got to be consistent feed, consistent solids. Okay, so the backfuge is another option for processing high P solids. Again, we use the backfuge for animal cells. It works very well. Doesn't work so well on yeast because they pack hard in the test tube, right? But again, I'm going to show you this animation again. I obviously like it very much, but it actually shows how the solids behave like a heavy phase liquid and continuously go over the top disc. And we're closing the bowl again. We're going to start our production. Separations made in the disc stack. The blue is your solids continuously going over what we call the top disc, continuously out of the machine. Clarified liquid up the center through the discs. And again, sometimes if you have like undigested media, you might have to discharge the machine every half hour just to clear whatever solids might have packed up at the wall of the bowl. This shows that similar 1G selling tank approach. heavy phase coming out one area, light phase coming out the other. And we have actually valves on both heavy and light phase, so we can push that solids over, or one way or the other, towards the solids to make it more concentrated, towards the liquid if we want more flow through the unit. Let's go to the next slide. This is a very small test unit we call the Explorer. That's a very tall Swedish guy. Proud of his design, obviously, but that unit, we told our top management, before a biotech customer is going to spend $1.5 million on a machine like this, they got to be able to test it at 100 or 200 liter. It's taken 5 years to convince them, but I think we're going to have a machine available January of next year. So the biotech guys can't afford to make a bad decision on their centrifuge choice. I mentioned that we have a single-use centrifuge in biotech. I don't know if you guys will be looking at the biotech industry after you get out, but everything is, or a lot of things are single-use now. Single-use bioreactors, just a big plastic bag, single-use pumps, single-use fittings. So now we have a single-use centrifuge, all plastic disc stack, plastic bowl. This is what it looks like. It's like the bowl's upside down compared to what I've shown you before, but tubes coming in, tubes coming out. This is the backfuge feature, which continuously allows discharge of the solids. We've gotten up to 90% solids coming off this unit in biotech. And for them, they don't care how dry the solids are, except that means yield for them. And this can be thousands of dollars, a gram in biotech. I mean, we all know how much crazy drugs are in biotech, right? So biotech guy uses this for 48 hours, pulls it out, throws it in the garbage can, gives us another $18,000 for a new bowl, and they don't even blink. I mean, it's for biotech. The problem in biotech is cleaning validation. It's very difficult to make sure that the vessel is clean, the centrifuge is clean. So it's all about cleaning validation, and that's why they go plastic now. Yep. Because this comes in sterile. They know it's sterile, but you can't, assure that your stainless steel tank or your stainless steel centrifuge or your stainless steel pump is sterile. You can't assure that. And if you do an inspection, that means you open it up, so then it's not sterile. So that it's all about validation and based on what the FDA tells you. So, yeah. I mean, the other thing is, back 20 years ago, the biotech guys had to have a 20,000 liter fermenter to make enough active drug. And now the cells are so active, they can do probably the same thing in a 2,000 liter. So that's the other part of the discussion here, right? And yeah, I mean, it's, and the industry asked us for like 15 years, where's your single-use centrifuge? And we fought it forever, but it's a great design. We see a big future. So just a quick discussion on centrifuge CIP. And normally you finish your run, tell you to rinse with cold water, 5-10 minutes, shoot the machine every couple minutes, get the bulk of the solids out of the unit. Some people choose to go to hot water and do the same procedure, shoot the machine a few times. But the key thing is caustic, 1 to 2% caustic at 70, 80 degrees C. And that's what really does the cleaning inside the bowl. After caustic, they might do another water rinse. They might do nitric acid. Again, these times are like maybe what a food customer would do. Biotech might do 2, 3, 4 times those just to make sure it's clean. Again, a stainless steel machine. The final rinse with water to make sure your pH is back to neutral. So that's the disc machine discussion. Again, it's a lot of information, guys. I don't, does it help? Yeah, okay. Well, let's talk about a little bit about decanters. So instead of in a decanter, the bowl being mounted vertical, it's mounted horizontally. When would you consider a decanter? Typically, a decanter sees high feed solids, 20% by volume, 30, 40% by volume. A decanter is what we call a dewatering machine. Most decanters are limited to 3,000 Gs, so they typically can't handle particles below 15 micron or below 15 micron. If it's real dense material, maybe might be fine, but most food products, 15 micron or larger. Decanters make a nice dry solids. They don't have to be fluid when they come out of the unit. So typically, if you spun the solids after the decanter, it's close to 100% solids on a test tube spin. They use these machines in wastewater, so they don't mind using polymer to agglomerate the particles to make them think they're bigger than they are. Some food grade guys don't necessarily use polymer; they use other additional things, help agglomerate, maybe pH adjustment, but if you don't want any additives in your material, then you probably don't want a decanter. So again, decanter, horizontal bowl, cylindrical section is where you do your separation. Your conical section is where you do the dewatering of the solids. You feed in through the feed pipe at the far end, comes into a feed zone, everything comes into the bowl. Your clarified liquid goes to the liquid end. If it's an open design, then it drops below the machine into a pump. If it's a pairing device machine, then you pump the liquid away. On the solids end, solids are conveyed up that what we call the beach area. That's where the solids are dewatered. The solids drop down below the machine, either into an auger or some type of real positive displacement pump to pump the solids away. You have a few things that you can vary form. So let's talk about a couple other features. The motor on the far right-hand side is the main drive motor that spins the bowl. That gearbox drives a differential between the bowl and the conveyor. We need a differential speed between the bowl and conveyor, otherwise we couldn't convey the solids. And that's driven by a motor to adjust the speed. So if you were just to hold that's called the sun wheel on the back of the gearbox, you'd see a differential speed between the bowl and conveyor of about 30 RPM. In some cases, we want to run lower differential than 30. So in that case, we would drive the motor in reverse to try to slow that differential speed down. If, say, sometimes we might want to run up to 60 or 50 RPM differential, then you just reverse the direction of the motor to drive that sun wheel the opposite direction. Okay, another animation there. This is going to show that's your feed pipe, that then on the end, that's where your feed is coming in. Feeding in through the feed pipe, through those openings. Clarified liquid goes to the solids are conveyed up the beach area for dewatering. Clarified liquid goes to the back end, either pumped away with a pairing device or drops into a pump below. You have adjustments you can make, either the differential speed, either make it faster or slower. You can adjust the pond depth inside the machine to make the solids wetter or drier. There's a lot more things to optimize with a decanter. Normally we test with what we call the Foodec 100, which is about an 8-inch diameter machine. And once we optimize performance, We can determine we want a 200, 300. We have a variety of sizes of machines. Big machines like the 800 are what we use in ethanol. Big, great big. I think they're like well, I think they're 800 diameter. Okay, 740 diameter machine. Big machines. Okay, so that's the discussion on decanters. Just a quick one because most of the time in biotech and food, you always see disc machines. We're just going to talk about some other products that Alfa Laval makes, and I'm going to make you watch a movie. Alfa Laval makes membrane systems, either spiral or flat sheet. We have test equipment. We make heat exchangers, plate type heat exchanger. We make evaporation systems, pasteurizers. We also have a division that makes pumps, fittings, valves, sanitary, what we call the sanitary equipment division. Also make tank cleaning equipment. Again, it's based around our key technologies, centrifuges, fluid handling, and heat exchange. We have a small lab unit called the M20. We can process normally between 5 and 50 liters of feed material. It can either be a flat sheet type of setup, or it could be a spiral type setup. We can do UF and MF, which is low pressure. We can do nanofiltration and reverse osmosis, which is normally 40 bar, 60 bar pressures, very high pressures. Normally to separate very small particles in membrane separation. Next size up is the pilot unit multi, and the multi-unit more of a production size machine. We can make as big a unit as you want. Alfa Laval is big in the heat exchanger business, from very small to very large. You need, wherever you need to either heat something or cool something, you might be able to do it in a plate heat exchanger. Make evaporation systems to evaporate the water out of a product. The larger scale unit there. So that's what I had to tell you guys about. I don't, kind of tough with the mask and tough when people can't talk. Any questions or any comments, or you guys ready to buy some centrifuges? Or so these are big production units, right? These are you know, normally for a research lab, I mean, most of our machines start at like 100 liter volume typically. Yeah. So like Pal Bio is what, 200 liters, something like 100, 200 liter. So, but below that, you know, we make a little solid bowl unit that you have to manually remove the solids. We could sell you that. That sells for like $22,000. That would mount on your table. But with that, you have, once you separate the solids, you have to manually remove them. You have to scrape them out of the bowl. So if you want to do tests, and Doug, you and I talked about this, if you ever came up with some material, I have a small continuous bowl. We could bring that in and make up some yeast and separate that and show you how that would work. But I got a little movie here, and it's kind of, it just kind of goes over all this probably in a more technical way, and it's from the 60s, so it's a little weird, but it's I think
Does it have sound?
it does have sound. Yeah. Okay. Could that be a problem, you think? Or yeah.
I think we just need to change the settings.
Okay. Okay. Bring it up here real quick, and then. Yes. Should be good. So, like I say, it's from the 60s, not the best quality, but good content. It's kind of funny, I think.
Oh, I think you have to change the share screen too.
Okay.
It's on the.
It's only about 10 minutes. It's not too crazy long. And it just kind of goes over the information very fast.
Gravity
Up there,
is
though.
a remarkable thing. One of nature's great mysteries. Nobody knows what it is, but everybody knows what it does.
You have to get rid of that other one.
Muddy water left standing cleans itself.
It's got the other presentation up there.
Solids sink to the bottom, leaving clear water on top. A simple matter of separation. Let's look at it this way. The blue globules represent the lightweight component, that is the water. And the grey ones, the heavy component, the solids. Once all the solids have settled to the bottom, separation is complete. The water can then be collected by pouring it carefully over the rim, by decanting it. This simple process of gravity separation is what we technical people call batch settling. It has been used, and still is used, for a great many purposes in industry.
Okay.
Innumerable purposes.
You guys can hear it okay?
Let's examine things carefully for a moment. In gravity separation, there are two major factors. One is time, the other is gravity. The time required to complete this settling process depends in turn upon two factors. Firstly, the settling speed of the particles. Secondly, the distance these particles have to travel before they actually settle. It is by reducing this distance that the separation process can be speeded up. Very simple. Now then, in order to maintain the same volume, it is not enough to make the vessel shallower. We must also make it wider. With a little ingenuity, the system can be arranged for what we call continuous flow. In other words, the mixture is fed into the tank at one end, and the lightweight component is discharged at the other. The particles then move in two directions, vertically downwards because of the pull of gravity, and horizontally due to the flow of the current. Now then, if properly arranged, a continuous flow system of this type will result in all the solids settling at the bottom and the liquid being discharged over the edge of the rim. But the rate of feed can't be speeded up, because then some of the solids would never reach the bottom. They'd be carried over the rim and discharged along with the liquid instead, which would be defeating our purpose. How can we get round this difficulty? Simple. We can insert a shallow tray in the tank, which has the effect of reducing the settling distance and thus the time required for settling too. We can go a step further. We can insert several trays at short vertical intervals from one another. Result, an efficient method of speeding up the settling, which we call thin strata distribution. It's possible to go even further in the application of gravity. Let's take the common case of trying to separate two immiscible liquids, oil and water, for instance. If the mixture is left in a simple batch settling tank, we shall soon find we have three layers. On the top, a clear layer, which we call the light phase. In between, a narrow layer of still unseparated feed material, which is known as the neutral zone. And on the bottom, the heavy phase. If the mixture is left standing long enough, the neutral zone will disappear, and in its place a diffused belt will be formed, known as the interphase. Just as in the case of solids, this process can be made continuous by providing the tank with one inlet and one outlet. But here we must have two outlets. Then, In order to keep the system properly balanced and the level constant, some sort of counter pressure must be applied to the lower outlet. By applying pressure in this way, it means we can keep the neutral zone at the level we want, which is what we call the balance column principle. What we have to do now is make the tank more practical at the outlets and the inlet. Let's have another look at it. The feed material is fed continuously through the inlet passage, after which it passes under the first baffle and on into the tank, where it forms a neutral zone. The light phase then rises to the top outlet. The heavy phase sinks towards the bottom and is discharged through the lower outlet. So far, so good. But now for a small refinement. To make the tank adjustable for different immiscible liquids, we can provide the lower outlet with a so-called dam. This dam serves a very useful purpose. If it's set low, the position of the neutral zone becomes low too, which means that there'll be a risk of some of the light phase escaping along with the heavy phase. But at least the bulk of the light phase will be discharged through the upper outlet. And if we set the dam high, we obtain precisely the opposite result. Let's see what all this looks like when we express it mathematically. Let's call the settling velocity V, and the density of a particle or globule of heavy liquid S. The density of the lighter liquid, S1. The diameter of the particle, D. The viscosity of the lighter liquid, mu. And of course the gravity acceleration, G. Then we can go ahead and write the formula. Now this is all very well, but what can be done to speed up the settling process? Can we do anything about the size of the particles? A little perhaps, but not very much. How about altering the densities? Unalterable, I'm afraid. Vary the viscosity. That is possible. If we heat a volume of heavy viscous oil, it becomes a thin, runny fluid. And what about this? Sorry, you can't change that. But if you replace G, the force of gravity, by centrifugal force, there's hardly any limit to what can be done. This is what Stokes' law means. By replacing gravitational force by centrifugal force generated by mechanical means, the constant factor G can be multiplied many thousands of times. Suppose we take a balanced tank and rearrange the component parts so as to permit a rotation. There we are. Now then, faster and faster and faster, the centrifugal force becomes greater and greater. Now let's see what happens inside the rotor, the so-called bowl, during the separation process. And how the liquids behave during a continuous separation process. We can see here that some of the light globules are escaping along with the heavier liquid, but that the bulk of the light liquid itself is absolutely clean. In order to capture these errant light particles, we use another discharge ring. This ring serves the same purpose as the dam in the balance column tank. In other words, it keeps the neutral zone just where we want it. Now, what happened when we increased the rate of the feed? It meant there was not enough time for separation to take place, didn't it? But let's take another look at our thin strata principle. We take a number of discs and put them in the bowl. There we are. But this answer is still not quite good enough, because the particles passing along the channels close to the center are only subjected to a small centrifugal force. The channels around the periphery are much more efficient. What can we do? Obviously, we should try to make all the channels equally effective. Well, here's one thing. We can turn the cylindrical trays into conical discs, and then alter the shape of the bowl to conform with the shape of these discs. A simple little idea, but important. And what happens during the separation process when we use these conical discs? Light globules still keep escaping along with the heavier liquid, but this time it's easier to capture them. All we do is move the neutral zone inwards and, of course, drill holes in each disc. The bowl is the most important part of a centrifugal separator. We put it on a spindle, provide it with a drive unit, connect this drive unit to a motor, and put on a cover. And the result is a disc bowl centrifugal separator. A machine of this type is used for what is known as intermittent service. In other words, at the end of each run, the cover is removed and the accumulated solids scraped out of the bowl. This is the basic type, and it's used for liquids containing a low percentage of solids, up to 1%. The bowl may also be made solids ejecting. The separated solid particles accumulate in the sludge space of the bowl, to be ejected at intervals by centrifugal force, when discharge outlets are opened around the periphery. Separators of this type are useful for liquids containing up to 6% sludge. In the nozzle separator, the separated particles continuously escape through nozzles around the bowl's periphery. These particles, for example the concentrate, may be recycled for further concentration. They often constitute valuable products worth utilizing. The sludge content of the feed may be up to 25%. A decanter can handle liquids containing as much as 40% sludge. The separated particles are discharged by a screw conveyor that is built into the rotor. Because of its capacity for dewatering liquids that are rich in sludge, the decanter offers a most useful tool for treating products that are to be dried subsequently. This, then, is the state of affairs today for centrifugal separators. But research and development continue. We are constantly discovering new fields where conventional methods and processes can be substantially improved, speeded up, and made more economical by the use of centrifugal separating machines. As their inventor, Gustave de Laval, said, "Speed is a gift from heaven."
A good review, huh? That's it, guys. Do your lab now.